Welcome to all in the lecture series of Functional Analysis 1. Now in this lecture we see the theorems related to linear operators. So firstly we see about the definition of injective or one-one linear operator. Let capital T from script d of t to y be a linear operator. Then capital T is injective or one-one if and only if tx1 equals to tx2 implies that x1 equals to x2 for all x1 comma x2 belongs to the domain script d of t, or x1 not equals to x2 implies that tx1 not equals to tx2 for all x1 comma x2 belongs to script d of t. This is the definition of the injective or one-to-one operator. The linear operator is said to be one-one if and only if images are equal, implies that points are equal, or another condition is that points are distinct, then their images are distinct. That is the definition of the injective operator. Now here we know that the linear operator capital T, which is from script d of t to script r of t, that is the range of the operator t, which is always contained in y. This linear operator is always an onto map. We always know that this linear operator is an onto map. But when this linear operator satisfies this condition or this condition, then this linear operator becomes 1-1. And when the linear operator is both 1-1 and onto, then in this case T is said to be bijective. That is injective as well as surjective, this operator. And when this linear operator is bijective, then in this case T inverse, and this T inverse it is from script r of t. Script r of t to dt exists. This inverse exists only when the linear operator is bijective. That means inverse exists. We have only to show that the linear operator is 1-1. When we show that the linear operator capital T, which is from dt to script r of t, is 1-1, and then in this case we directly get that the T inverse exists, because the mapping T, which is from dt to script r of t, it is always an onto map. In this way we see the existence of the inverse of the operator T. Now after this inverse operator, we have the theorem about the inverse operator. The statement of the theorem is: let x comma y be the vector spaces both real or both complex. Let capital T from script d of t to y be a linear operator with the domain dt subset of capital X and range script r of t subset of y. Then we have to prove this three statement. The inverse T inverse, which is from script r of t to dt, exists if and only if tx equals to 0, implies that x equals to 0. The second statement is if T inverse exists, it is a linear operator. And the last condition is that if the dimension of the domain dt it is equals to n, which is strictly less than infinity, and the inverse exists, then the dimension of the range, that is script r of t, it is equals to the dimension of the, that is the script d of t. Now here, so firstly we prove the first statement, that the inverse exists if and only if tx equals to 0, implies that x equals to 0. So firstly we assume this part and we prove this part. That means here suppose tx equals to 0 implies that x equals to 0. That means we consider this part, and now we have to prove the existence of T inverse. Then we have to show that T inverse which is from script r of t to dt exists. That is we have to prove. Now to show that the inverse exists, we know that the inverse exists if and only if the given mapping which is from script d of t to script r of t is both 1 1 and onto. If the linear operator is both 1 1 and onto, then its inverse exists, and it exists, that is we have to show that the mapping T which is from script D of T to script R of T is 1 1. To prove that the mapping is 1 1, we show that if the images are equal, points are equal. So we start with any 2 points of the domain. Let x1 comma x2 belongs to the domain script D of T such that their images are equal. That means such that tx1 is equals to tx2. Now we prove this statement. That is tx1 is equals to tx2. tx1 is equals to tx2 implies that tx1 minus tx2 it is equals to 0, and we know that capital T is linear, and as capital T is linear implies that T of x1 minus x2 it is equals to 0. But here as the given condition is that T of x it is equals to 0 implies that x equals to 0. Here we have T of x1 minus x2 equals to 0, and then by given condition implies that x1 minus x2 equals to 0, and this implies that x1 equals to x2. We start with that tx1 equals to tx2, and we get that x1 equals to x2. This implies that the mapping T which is from script D of T to script R of T, the mapping T which is from script D of T to script R of T is 1 1, and we know that this mapping is always an onto map, and this implies that the T inverse which is from script R of T to script D of T exists. We start with that tx equals to 0 implies that x equals to 0, and we get that its inverse, that is T inverse from script R of T to script D of T exists. Now in conversely we assume that inverse exists, and we have to show that tx equals to 0 implies that x equals to 0. Conversely, suppose T inverse which is from script R of T to script D of T exists. We have to show that tx equals to 0 implies that x equals to 0. That is we have to show. As here given that as T inverse which is from script R of T to script D of T exists. Inverse exists implies that the mapping is both 1 1 and onto, implies that T from script D of T to script R of T is both 1 1 and onto. As the mapping is 1 1, this implies that tx1 equals to tx2 imply x1 equals to x2. The reason is that since capital T is 1 1, for any x1 comma x2 belongs to the domain. That means if the mapping is 1 1, then the images are equal implies that points are equal. Now here in this here we put the value of x2 equals to 0. By putting x2 equals to 0, we get tx1 that is equals to tx2. Now the value of x2 equals to 0, that means here we get t0, and the image of the 0 element, it is always 0, and therefore here we get that tx1 equals to 0. Now tx1 equals to 0 implies that x1 that is equals to x2, but the value of x2 equals to 0. That means here we get that is tx1 equals to 0 implies that x1 equals to 0. This means that if the mapping T inverse, which is from script r of t to dt, exists, then we get that tx1 equals to 0 implies that x1 equals to 0, and hence we prove the converse part. In this way we prove the first statement of this theorem, that the inverse T inverse exists if and only if Tx equals to 0 implies that x equals to 0. Now we have to prove the second statement. The second statement is, if T inverse exists, comma, it is linear. That is, we have to prove. The given operator is a linear operator, and we have to show that if its inverse exists, then that inverse is also linear operator. Now to show that its inverse is a linear operator, we have to verify all the conditions of the linear operator. So we start with the given condition as, let capital T from script d of t to script r of t here be a linear operator. Also, the given condition is that T inverse exists. Also, T inverse, which is from the range script r of t to script d of t, exists. As the T inverse, which is from script r of t to script d of t, exists, implies that the linear operator, which is from script d of t to script r of t, is both 1, 1 and onto. It is both 1, 1 and onto. As the mapping T, which is from script d of t to script r of t, it is a linear operator. As it is a linear operator, then by definition of the linear operator is that its domain is a vector space and range lies in a vector space. That means this range lies in a vector space and domain is a vector space. But in last lecture we show that if T is a linear operator which is from script d of t to script r of t, then its range is also a vector space. We prove this statement in the last period, that the range is also a vector space, and therefore as capital T, which is from script d of t to script r of t, is a linear operator, implies that script d of t is a vector space and by theorem, that theorem is 2.6.9 of the Irwin-Kreyszig group, and by theorem the range script r of t is also a vector space. It is also a vector space. Now the script r of t is a vector space. As a script r of t become a vector space, therefore the first condition of the linear operator is that the domain is a vector space, and this is the domain of T inverse, and here we get that the domain is a vector space and range, that is always a vector space, and then the first condition required for the operator T inverse to become a linear operator is that its domain, that is the script R of T, is a vector space is satisfied, and therefore the T inverse whose domain is a vector space is satisfied. Now the another condition, we have to prove its linearity. So we start with any two arbitrary point of this script R of T. We are taking let y1 comma y2 be any 2 points of script R of T. Now as these are the points of the range set, this implies that this y1 must be equals to tx1 and y2 that is equals to tx2 for some x1 comma x2 belongs to the domain script D of T. As y1 is equals to tx1 and y2 is equals to tx2, and here we have to given that T inverse exists and T inverse exists. As T inverse exists, therefore we may write it x1 equals to T inverse of y1 and x2 that is equals to T inverse of y2. That is the therefore we are getting the value of x1 and x2. Alpha y1 plus beta y2, where alpha and beta be any two scalar. Then alpha y1 plus beta y2, it is equals to alpha, putting the value of y1 that is equals to tx1 plus beta tx2. As t is a linear operator, therefore we may write it as t of alpha x1 plus t of beta x2. Again t is a linear operator, therefore we can write it as capital T of alpha x1 plus beta x2. That means here we get that alpha y1 plus beta y2 that is equals to capital T of alpha x1 plus beta x2. And here again T inverse exists. This implies that T inverse of alpha y1 plus beta y2 that is equals to alpha x1 plus beta x2. Now we are putting the value of x1 and x2, that is equals to alpha, the value of x1 equals to T inverse of y1 plus beta into T inverse of y2. That means we get that T inverse of alpha y1 plus beta y2, it is equals to alpha T inverse y1 plus beta T inverse y2. In this way, this is the condition for the linearity. In this way, we get that the operator T inverse, which is from script R of T to script D of T, is a linear operator. Is a linear operator. In this way, we prove the second statement of this theorem. Now we have to prove the third statement. The third statement of the theorem is that if dimension of script D of T that is equals to n, which is strictly less than infinity, and T inverse exists, then dimension of script R of T, it is equals to dimension of script D of T. That is we have to show. Now to prove this theorem, to prove this statement, we use the statement of previous theorem which we proved in last lecture, is that if T is a linear operator, we write down this statement here. If capital T, which is from script D of T to script R of T, is a linear operator, and if the dimension of dt dimension of script d of t equals to n, which is strictly less than infinity, then the dimension of the range set, that is the script r of t, it is less than or equals to n, and n is nothing but dimension of dt, dimension of script d of t. Now we use this theorem here to prove this equality. As here we have to given that the dimension of script d of t equals to n, which is less than infinity. Again here in the given condition we have to given that the operator t, which is from script d of t to script r of t, be a linear operator, and therefore from these two conditions, as t from dt to y be a linear operator and its dimension of dt it is lesser than infinity, then by using this statement here we get that. Now see in proof. As capital T, which is from script d of t to y, be a linear operator, and also given that dimension of dt equals to n, and dimension of script d of t, that is equals to n, which is less than infinity. Then by this theorem, we get that the dimension of script r of t, it is less than or equals to dimension of script d of t, if we give it the name 1. Now again, also here we have to given that T inverse exists, as T inverse. Now the mapping T inverse, it is from script r of t to script d of t exist. But in the second statement of this theorem, we have to given that if the T inverse exists, then it is linear. As T inverse exists implies that T inverse, which is from again script r of t to script d of t, is a linear operator. Now we use this theorem again, as it is a linear operator and its domain is now script r of t and dimension of script r of t. Now here the dimension of script r of t, from equation 1 we have to given that the dimension of script r of t, that is less than or equals to the dimension of script d of t, and here the dimension of script d of t, it is equals to n. It is equals to n, which is less than infinity. That means here the dimension of script r of t, it is less than or equals to n. That is dimension of script r of t, that is less than or equals to n, and this is lesser than infinity. Therefore here we get that that is T inverse, which is from script r of t to script d of t, is linear, and the dimension of, now its domain is script r of t, and dimension of script r of t, it is less than or equals to n, which is strictly less than infinity. This implies that by using this again the theorem, this implies that the dimension of here the codomain is dt, and therefore we get that the dimension of script d of t, it is less than or equals to the dimension of the domain, and the domain is script r of t. Now we give it the name equation 2, and therefore from 1 and 2 we get dimension of script d of t, that is equals to the dimension of script R of t, and hence we get the result that the dimension of script R of t, it is equals to the dimension of script D of t. In this way we prove the theorem about the existence of the linear operator. Also we prove its dimension of the domain and codomain. If it is less than infinity, then the dimension are equal.